and they even contain adversarial examples. So in practice, this is the image by ChatGPT that takes the algorithm takes the internet, cleans it up, and then produces a nice classifier. So in practice, there's data distillation, but here we care about the computational complexity. So the question is, how does data contamination influence the computational complexity of learning? And of course, this is a very old question. It dates back to the 80s. So let's see what the one standard model is there. So let's say that there is a clean distribution out there in the world that generates labeled data. We're just considering supervised learning, classification in particular in this talk. So there is a clean distribution that generates labeled data. The marginal distribution of the features X is just a very nice distribution, D star. And the labels are generated by some classifier, F star, that lies within a known concept class, some function class F. So there is this clean distribution, it generates IID data, but now there is an adversary that receives this data set and substitutes an eta fraction of the data set with an equal number of adversarial points. Both X and Y can be adversarial in these examples. Now the learner receives this data set and is trying to output a hypothesis whose error on the clean distribution, so D star, F star, is at most 2 times the contamination rate. So this 2 there is information theoretically optimal because essentially we have to pay for both the examples that we don't see and the examples that are adversarial. Okay, so the goal is that, so hopefully this is clear. But please ask any questions if they arise. Yes?
Does the adversary have access to our learning algorithm or not?
The adversary can have access to the learning.
He also knows what we are going to do, right?
Yeah, I think so. Yeah. So here's another definition, which is kind of the way we'll present it is incomparable, but it's a stronger definition of heavy contamination, where once more there is a clean distribution. Now we will not assume anything about the labels just because it will not make the problem easier. So let's just say that the labels are arbitrary. But the distribution is clean meaning that X comes from IID from some nice distribution D star. Once more we have the independent data, and then the adversary adds a very large number of adversarial examples, X, Y. And now there is just maybe, let's say, 50% of the data are clean, and the remaining 50% is adversarial. So this is the contamination ratio Q, which is essentially the total number of examples divided by the clean examples. So if we're 50% clean, then Q will be 2. Okay. Now let's see what can we hope to achieve as an error benchmark here when we have such an input data set. So op total is the minimum error some classifier in our class can achieve on this input data set. So op total is just the data dependent quantity, which is the error on this data set by some hypothesis in our class. And our goal is to output some hypothesis whose error on the clean distribution is Q times op total plus epsilon. So we have to rescale op total with the contamination ratio. And the reason for that is, this is necessary. We have to do this rescaling. And to see this, let's say that Q equals 2, right? The adversary can just duplicate the examples with the opposite labels. So even if the initial distribution was realizable, you will not know whether F star is the ground truth or minus F star is the ground truth. So you would have to pay error 1/2, even though your initial distribution was realizable. Okay, does that make sense?
So, should I think of uptotal as a empirical quantity?
Empirical quantity on the
Contaminated.
Yeah,
on the
so
contaminated samples.
right.
All
So
of them.
that depends. So that okay. So it's not. So it's like you wanted. If there is uptotal, you want to get the
Yes.
I mean, it's just confused because there's some things are on the population and these are.
Yes, this is just the on the data set. So Q of total is total number of errors that the best classifier makes divided by the size of the clean data set. So we're paying for all the errors in the clean data set.
In this model, there's no deletion.
There's no deletion because if you had a large fraction of deletions, then this would be learning with truncation. But you can add like a small number of deletions, as in this model, and then it would be formally stronger. Okay, so this is the two problems. Here F star achieves optotal, here F star generates clean labels. Their benchmark is 2 eta, here it's Q times optotal, and we are in high dimensional feature space. So D is large. Okay, and just interpretation, so this is where an adversary has limited budget. So the adversary can only target, let's say the data set is distributed across different servers, and the adversary can only target a bounded number of fraction of the servers. But here, this looks more to me like the internet. So it's maybe there is something that explains all the data, like some classifier that classifies the data in internet well, but the data are not structured at all. So the features are there still could be some structure in there. Okay. So information theoretically, if we focus on just classes with F with bounded BC dimension, the ERM solves both of the problems, and this is just because if the number of mistakes that the ERM makes on the input dataset is at most 2 times eta here, and at most Q times the total here. Okay. Our question is, how does contamination influence efficient algorithms? Right? Because we know that structure is crucial for efficiency. Even for very simple problems, where F is the class of linear or affine separators, unless you have some structure in the data set, then the learning problem becomes hard if there is noise in the labels. Okay, so we know that structure is crucial for efficiency, and we don't know if contamination just completely removes this structure. So what do we know? We know for adversarial label noise, where the adversary can only change the labels of the input data points, but not change the points themselves. We know that in terms of computational complexity, if there is a low degree polynomial, if there are low degree polynomials that approximate the ground truth function in expectation under our input distribution D star, then we have efficient learnability just by running a polynomial regression. So these are standard results that low approximation degree in this sense implies efficient learnability in under label noise. And actually for statistical query algorithms, this condition is actually necessary. So with some caveats, but yeah, with some caveats. But for most interesting classes like half spaces or neural networks, this condition is necessary. Okay. So just as an example, the degree, if the degree of the class is L of epsilon, so if you want to achieve epsilon is this epsilon. So if the degree is L of epsilon, then the complexity, the time complexity for learning is D to the L of epsilon. And for DNFs, this gives a quasi-polynomial time algorithm for monotone functions gives a sub-exponential algorithm. So these are non-trivial algorithms. They're not polynomial, fully polynomial time. Okay. But that's the best you can do in general. Okay. So what do we know about that? That was for adversarial label noise, but in bounded contamination, much less is known. So all known results either lead to exponential dependence on the input dimension or hold for special classes and achieve suboptimal error guarantees. So there's the work of ABL that works for origin set of half spaces and achieves order eta, not 2 times eta, works for local distributions, and then a bunch of other works. Like note here for intersections of half spaces, if K, which is the number of half spaces, is D equal to the dimension, then the error guarantee is trivial, because if you want to get anything out of it, you would have to choose eta to be less than 1 over d to the 4. And this is trivial. You would never see any contamination because the number of samples you need to learn is much less than d to the 4. Okay, so for example, as a concrete example, there's no quasi-polynomial-time algorithm for polynomial-sized DNFs, which are just depth-2 circuits, with respect to the uniform distribution of the hypercube for bounded contamination, but there was for adversarial label noise. Okay. So the first question, naturally, is whether low approximate degree suffices for learning with contamination. Now, for heavy contamination, I think, at least to the best of my knowledge, the classification under heavy contamination was not studied at all before. What was studied under heavy contamination is unsupervised learning and linear regression. But even then, the results fall in these two categories. One is list decodable setting, where the algorithm will output a list, and only one of the elements of this list is guaranteed to be a good hypothesis. But we don't know which one. And the second one is the semi-random models, where there is some kind of, there is an adversary that adds a lot of adversarial points, but information theoretically the adversary is monotone in the sense that it only helps to give, it gives more data, more information, but these data just break the assumptions that lead to efficient learnability. Here, none of these are true. So we will, first of all, we just output a single hypothesis. And second of all, even information theoretically, we will see by the end of the talk that the heavy contamination adversary actually harms even information theoretically. Okay, so the second question is, when is efficient learning possible under heavy contamination? Okay. And now the results we have for bounding contamination are that approximation degree implies efficient learnability under bounded contamination. This resolves the gap between the computational complexity of learning under adversarial label noise and under heavy contamination, under bounded contamination. It gives new results for many classes. I mean, apart from the approximation property, which holds with respect to D star, we also require that D star itself has some nice structure, it's hypercontracted, for concentration properties. Okay, but what are the new results we obtain? For monotone functions, the exponential runtime, which is a trivial one, becomes sub-exponential. For DNFs, the exponential runtime becomes quasi-polynomial. And for intersections where the best error guarantees were trivial, we just get a quasi-polynomial-time algorithm with optimal error guarantees. And for heavy contamination, we use a stronger notion of approximation. So, as we will see, just approximating polynomials are not sufficient for learning under heavy contamination. So here we use this stronger notion of approximation, where it says, you have a function, f star, and you ask for two polynomials. One is above, always above, point-wise, and the other one is always below the function, point-wise. And their expected difference under the distribution D star is small. So this is the approximation, the sandwiching polynomials. This notion originates to pseudo-randomness, where it's equivalent to folding via moment matching, but we will not use this. What we will use is this celebrated result that has a long history in the pseudo-randomness literature. It's the first was proven a special version of this by Bazi, then Razborov simplified the proof, and then Braverman generalized it. And so the result is that sandwiching degree of circuits of constant depth is polylogarithmic. Okay. So we should note here that sandwiching degree can be much smaller than approximation degree. And in particular, for monotone functions with respect to the uniform distribution, the sandwiching is linear, but the approximation degree is root p. But regardless, what we showed is that if you have sandwiching approximation, then you have efficient learning under heavy contamination. And once more, this implies several results. Okay, so these are the results. Let's see how we got there. So recall that for...
One question.
Yes.
Can you show that this is necessary for statistical queries? Similar
Which,
to
for the sandwiching degree? No. What we can show is that, and we will show, is information theoretically, approximation degree does not suffice. So something more is needed, but we don't know if sandwiching, although we have to go all the way to sandwiching. So for label noise, the algorithm idea is simple, and it's saying, if there is a polynomial that approximates your ground truth function under the input distribution, then just run polynomial regression, and you will find a polynomial that outcompetes this approximator. The concern now is that due to contamination, there is no polynomial that approximates our function, f star. So even if we run polynomial regression, maybe we get garbage. So what we will try to do is find a filtered subset where the polynomial approximation property with respect to f star holds, but we want to keep almost all of the clean examples. So we don't want to remove a lot of clean examples in the process. And conceptually, the way we will do this is in these two steps. So first, we will reduce the polynomial approximation property of the ground truth, f star, to just some property about polynomial approximators, polynomial expectations. So instead of considering expectations of f star when it's some polynomial, we just consider expectations of polynomials. So that's the first step. And then the second step is just to remove outliers using some polynomial filtering method that ensures the preservation of polynomial expectations. So I will be more precise, but that's morally what we're doing. And to see this, let's just consider these sandwiching polynomials. And this is why, so sandwiching polynomials are very strong in that the first step, which is showing that preserving polynomial expectation suffices, becomes trivial. Okay? So observe that if the expectation of p up minus p down over any sample S is small, then we immediately know that p down is a good approximator for f star. Because f star is always between p up and p down. So we just need to insert this polynomial approximation property, and then we have the f star approximation property for free. This is just a very simple observation.
Sorry, S is a training set, right?
This is any set. This is just an observation that says, for any set, if the expectation is small, then also. So our goal is to find some filtered set where this property holds, and we don't remove a lot of clean point examples due to this. Okay, so that's what we want to do. Preserve the expectation of p up minus p down by only removing points that are unlikely to be clean. This sounds a lot like outlier-removal techniques from robust learning. This is what they're trying to do. There are two caveats. So usually these results focus on squared polynomials, not just, and p up minus p down is not necessarily squared. And secondly, the bounds on the expectation, at least in the results that I've tried to use as a black box, the bounds on the expectation in the end become worse with the degree of the polynomials. But the degree of this polynomial, p up minus p down, depends on the approximation property. So expectation p up minus p down is epsilon if the degree of p up minus p down is large enough with respect to epsilon. And this leads to race conditions. So at least it seems that we cannot apply black box outlier-removal techniques. That doesn't mean we came up with some very complicated algorithm. We just had to be very careful in the choice of the algorithm. So the choice of the algorithm is this. We just try to find a polynomial whose empirical expectation on the input is much larger than its absolute expectation under the clean distribution. So we try to find such a polynomial, and then we remove the points x that give this polynomial large values. So what do we know about this polynomial? We know that its values under the clean distribution are usually small. Otherwise, the absolute expectation would not be small. But we also know that under the empirical distribution, the expectation of this polynomial is large. So there must be many points that give this polynomial large values. Otherwise, the expectation would also be small. Okay, so we remove the points from the input that give this polynomial values larger than threshold. And actually what we can show is that there is some threshold, such that if we condition on p of x greater than the threshold, the outliers are more than inliers. So every time we remove points, we remove more bad points than good points. More adversarial.
This has nothing to do with the labels. This is just about...
Yes, this is just about polynomial.
Is this where you need hypercontractivity?
You need, there are several things I have pushed under the rug, but there is concentration properties and yeah. Yeah. Okay, so the guarantees we obtain is that for any polynomial whose absolute expectation is small under the clean, the expectation under the filtered is small, so that's the polynomial preservation property. And secondly, the algorithm removes more adversarial points than clean points.
What's Q, sorry?
Any polynomial.
Oh.
With some bounded degree. Okay. So using these guarantees, we immediately obtain this theorem that says that sandwiching degree implies learning under bounded contamination. And this is just because we can apply these results on this p up minus p down polynomial. And then we have a filtered set that contains almost all the clean examples, because the number of clean examples removed is bounded by the number of adversarial examples, which is small. And also, this filtered set respects the polynomial approximation property with respect to f star. So polynomial regression works.
Excuse my question.
Yes.
So suppose I have a data set with half of data is clean, which underlying data is a linear classifier, and the rest half is a opposite classifier. In this case, how could the algorithm find so-called outliers since they are almost the same?
Sorry, so this is for bounded contamination. So the number of adversarial points is bounded by eta.
Yeah.
The fraction is bounded by eta, and eta is small. So it cannot be the case that half of them are
Okay.
adversarial. So maybe I do not understand the question.
Okay. So in this case, eta is small.
Okay. Now let's go to heavy contamination. The same approach works essentially. The same algorithm, we just are much more selective in how we remove adversarial points. So instead of saying, oh, the expectation under the clean is epsilon, but the empirical expectation is 10 epsilon, we're saying that the expectation under the clean is epsilon squared divided by q. So this means that every time we remove points, we remove q over epsilon times more adversarial points than clean points. And this means that even if we end up removing all the adversarial points, we will only have removed epsilon fraction of the clean points. So again, we remove. What we pay is that we have to begin with. We need to begin with a better approximation property.
Maybe just, but I think this question.
Yeah.
If in the event that what the adversary chose to do is just make copies of the examples with the opposite labels, in this case, no points would be removed because they're all the marginals are all the same. But that's okay because
this is encoded in the information theoretically. Their benchmark.
Since the goal is just q times is.
In the heavy contamination, the goal is q times op total. So we would pay for that. That would be 1/2.
In other words, I think I'm interested in whether this result can address the learning of the clean distribution, because it looks like we somehow modify the criterion to q times of OPT total, which is evaluated on the contaminated dataset instead of the underlying tubes. In other words, is that possible to still learn the clean data in terms of heavy contamination?
I'm not sure I understood the question. Yeah, could you?
Or using the previous example, if our interest is still on the clean distribution.
Yeah, their guarantee on the clean distribution.
Then the learn algorithm, how could we evaluate its distance from the clean distribution?
That's a good question.
Do you want upper bound on the clean error that's based on the clean error of the best fund? I mean, this gives you an upper bound on the clean error based on the total, the smallest total error. If you want something where the upper bound, the clean error is at most, say, some multiple of the best clean error,
that's
impossible.
That's impossible. Because the adversary, your example, right? The adversary can just flip the labels, so you don't have any information. Even if the ground truth is realizable, you don't know if it's F star or minus F star. But the guarantee here is on the clean distribution. It's just that the benchmark comes from the error that you can achieve on the contaminated distribution. And that's the best you can hope for. You cannot avert them. Okay. So the question, back to the question that we promised we will answer, is if low approximate degree is sufficient for learning with contamination. Now, we have this nice outlier-removal property, but we don't have sandwiching approximators. So remember, we can reduce the approximation property of F star to a property about polynomials if we have sandwiching polynomials. But we can also do that if we have approximating polynomials. But what's the choice for Q? Well, we choose this polynomial Q of x to be, if P star is the polynomial approximator for F star, the Q of x is P star squared minus 1. Now this polynomial, so this polynomial approximates a function F star, which takes values plus 1 or minus 1. So therefore its square should be close to 1. Right? So absolute expectation of Q of x is small. And we also show that if the expectation of this polynomial under the filter distribution is small, then that's sufficient. So you only need to essentially this comes from the fact that you only have boundary contamination, so the only problem, what we say here formally, is that the only problem that can arise is that P star of x takes some huge values, and we're ruling this out by saying that the expectation of this polynomial is small. And but focus that here, it's like the analysis is tight, so we use this polynomial to obtain 2 eta plus epsilon. If we just used P star squared of x, we would still obtain something. I think would be root eta. But this polynomial is important to obtain the actual information theoretically optimal guarantee. Okay, so can we do a similar thing for heavy contamination? Can we try to find some polynomial or something? No. And the reason is that approximation degree does not suffice for learning with heavy contamination. And let's consider the favorite class, my favorite class for lower bounds, monotone functions over the Boolean hypercube. So monotone functions are the functions that preserve the hypercube ordering. So if points x and z, are comparable if all the coordinates are comparable with the same ordering. And note that what the adversary can do, even if, so we're trying to learn a monotone function with two heavy contaminations. So half of the data are clean, half of the data are adversarial. And we show that this requires exponentially many samples. Okay, why is that? Well, the adversary, let's say the ground truth is +1 or -1. So let's just keep one of these sets. So the ground truth is either +1 or -1. For each example x +1, the adversary draws a random z from the hypercube and gives the label -1. Okay? So the point is, we don't know if the ground truth is +1 or -1, but there is a monotone function that is consistent with all the examples, unless the number of examples is exponentially large. Why? Because the probability that x and z are comparable is exponentially small. So we need exponentially many examples to find a pair that is comparable.
The adversary is supposed to give his or her examples in such a way that it does not immediately violate monotonicity, right?
It doesn't violate monotonicity.
He must do it, yeah?
Not necessarily,
knows.
but the point here is that our error will be 1/2 because we have no information, but the op total, which is the error benchmark, is 0. Even if it was 1/4, it would be something, but now it's 0 and okay. So as a recap, for bounded contamination, polynomial approximation suffices. For heavy contamination, sandwiching approximation suffices, but polynomial approximation does not suffice for information theoretical reasons. And both of these upper bounds follow from the same outlier-removal guarantee. Okay. And just to give a broader context on what I've been working on, so I'm interested in strong learning guarantees under weak or at least verifiable assumptions. And assumptions in machine learning are everywhere, but there's a bunch of questions we can ask. So can we verify them? That's called testable learning. It was defined by Ronit Rubinfeld and Arsène Vassilian. Then another question is, can we relax the assumptions if we don't consider brittle worst case scenarios? That's smooth analysis for learning. Or can we guarantee low test error in the presence of distribution shift? That's called testable learning with distribution shift. And more questions. But let's focus on two of these questions that are relevant to what we talked about here. Testable learning and testable learning with distribution shift. So testable learning asks the algorithm to check whether the input distribution is structured enough for efficient algorithms. Learning with heavy contamination can be interpreted, not formally interpreted, but morally interpreted, to finding a subset of the input samples that is structured. So it's a finding version of testable learning in some sense. And for both of these problems, sandwiching suffices, but standard Boolean approximators do not suffice. And let's see now this other problem of learning with distribution shift, and see an analogy between these two worlds. So here's a motivating example. So we have some hospital A, and we have label data from this hospital. So we have the patient medical records and the outcomes of treatments. And for hospital B, we only have the medical records. We want to use data from hospital A to decide treatments for hospital B. So we need some guarantees. We cannot apply just a learning model for this. Okay. So TDS learning, testable learning with distribution shift, asks whether the evaluation distribution is similar to the one that I have trained on. There is this other model that predated our TDS learning model that was a finding version of this problem, saying, find a subset of the test examples that are similar to training data and only produce predictions for these. And what we showed is that outlier removal can be used to extend results we had for TDS learning to PK learning. And actually, this was what motivated us to go back to learning with contamination, because it was the finding version of testable learning. And actually, we first proved a result for a new learning problem, and then it gave us a result for an old learning problem. And then this is just a slide with results we have in TDS learning. It's just that morally we're trying to just bring all the learning theory guarantees in the distribution shift setting in a certifiable way. And some questions there are whether we can produce a low error hypothesis even if there is a bounded amount of distribution shift, or some benign distribution shift. Okay, so open questions for these problems. One question that I really find very important is the outlier removal technique we used required access to this target distribution D star. So we had to commit to D star, unlabeled examples, but we had to commit to some D star and say, the expectation of P, of absolute value of the polynomial under D star has to be epsilon. That was a constraint. So we had to commit to some distribution D star. Can we have a universal version of this, where we don't need to commit to D star, but just a class of distributions? And say, if my distribution is log k, or I don't know, some kind of distribution, then we can have similar guarantees. And another question is, so for bounded contamination, there are these nice results with suboptimal error guarantees, but more efficient algorithms. So can we do something similar in the heavy contamination setting? So with that, some references, and thank you.
Questions?
Mm-hmm.
So for the filtering procedure, you needed the sandwich property and hypercontractive distribution, right?
For the filtering procedure, we don't need sandwiching. To apply the filtering procedure, we need sandwiching. We use sandwiching for heavy contamination.
Do you have any reason why do you need the distribution to hypercontract? Like, how do you do that? If there is a simple explanation.
I don't have a proof that says you need it, but essentially when you want the expectations of polynomials of arbitrary degree to to convert to concentrate, it just helps a lot.
So I'm still trying to understand this relationship between what you call find and
Yes.
what is that?
Yes, it's not. It's a moral.
So can you think of it in some sense that whether you're testing something globally or just telling you a single bit of it, is it fine or not, versus more locally, like identifying for each point separately whether it's fine or not?
Yes,
is
it's
that
for each point separately, but also that's more in the PQ learning setting where you classify every point separately.
Is that also? Can I understand that the same way? Also.
Well, for heavy contamination, you need a bunch of points to one point does not suffice. one Gaussian point does not suffice. So you need a bunch of points that
Right.
that together are structured, so you can actually run an efficient algorithm.
See, so this doesn't. So are there at the end of this? So are there gaps between the like, I guess I still don't completely understand.
Yes.
This view, but are there gaps between the find and the test then?
Actually, I think there is. There are some gaps. They're kind of technical. I don't believe in them. But one thing that is actually in upcoming work the group is that if you have TDS learning in the distribution-free setting, so you don't commit to a particular training distribution, then you can also have peaky learning, distribution-free. So there are questions there. I mean, in the distribution-specific setting, I don't know. In the distribution-free, it seems that they're not much different.
One thing you said, beginning you're thinking about. So I guess one way to think about at least some of your results is these are guarantees that if you had an ERM oracle, you would just get automatically, but can you do it efficiently?
Yes.
The 2 times zeta
Yes.
or the Q, whatever. This is, if I was able to run ERM in my data set, I would get it, but just, how do you do that? Is there hope for some kind of guarantees that might be even stronger than what ERM would give? Like that maybe if you knew there was this bad data, you wouldn't want to run ERM because ERM doesn't try to distinguish the good points and bad points. It's just, whereas some fancier algorithm might say, hey, I've got reason to believe these other points are bad, and or something like that. Is there hope for some thing?
I have a very unsatisfying answer, which is that yes, but the only example that I can think of is if you want to improve the 2 eta to eta. So if you want the error guarantee to be eta, not twice, or something better, then maybe it seems ERM just gives 2 eta. So maybe you have to, because essentially, I'm being very vague here, but if you want 2 eta, you would have to somehow calibrate your uncertainty in some way, so that you don't completely pay for both the points you don't see and the points that are added. And you might actually have to output, to do this, you might actually have to output a randomized classifier, not just a function. Yeah, but that's quite unsatisfying answer.
With the monotone functions, isn't that already an example that you can't rely on ERM?
It's an example where I guess I'm not sure if ERM works or not. That's why.
Because here you don't have uniform.
It's uniform. It's distribution specific. Sorry,
Yes.
This is unfair. We talked about this before, which is so distribution specific. So ERM might not be optimal there. In fact, it probably is not. Okay. I'm sorry. Any additional questions? Last question.
Could it make sense to relax the sandwiching requirement to say that, to have maybe asymmetric degree requirements for the 2 polynomials that maybe like the lower polynomial is supposed to have degree d and the upper one can have degree d squared. Or do you really need kind of both of them in the same way in the analysis, both the degrees?
I mean, it seems that we pay the degree of their difference in the analysis.
That would be both.
Okay. Let's thank Kostas again. And Kostas will be here throughout the day and tomorrow. You want to catch him?